After studying this module, you shall be able to know various models under sequential moments restrictions, models with individual specific slopes, also GMM approaches to linear unobserved effects model, and how to apply panel data methods in case of match pairs and cluster samples. Let us start with unobserved effects models without strict exogeneity assumption. First, we would introduce models under sequential moments restrictions. The assumption of strict exogeneity rules out certain kinds of feedback from YIT to future values of XIT. Generally, random effects, fixed effects, and first differencing are inconsistent if an explanatory variable in some period is correlated with UIT. While the size of the inconsistency might be small, in other cases it can be substantial. Therefore, we should have general ways of obtaining consistent estimators as n tends to be infinity or large, with t to be fixed when the explanatory variables are not strictly exogenous. The model can be written as YIT is equal to XIT beta plus CI plus UIT, where T subscript varies or takes the values from 1, 2 to up to capital T. This is our equation 1. Here in this model, we allow Ci to be arbitrarily correlated with XIT and UIT to be correlated with future values of explanatory variables, which are XIT plus 1, XIT plus 2, XIT, capital T. There are many models, including the AR1 model, or it is reasonable to assume that UIT is uncorrelated with current and past values of XIT. As per Chamberlain 1992b, sequential moment restrictions are where expected value of UIT given XIT, XIT minus 1 up to XI1 and Ci is equal to 0, where T takes the value from 1 to capital T. This is our equation 2. When assumption 2 holds, then XIT are sequentially exogenous conditional on the unobserved effect. So given model in equation 1, assumption 2 will be equivalent to expected value of YIT given XIT, XIT minus 1 up to XI1 and Ci is equal to expected value of YIT given XIT, Ci equal to XIT beta plus Ci. This is our equation 3. This equation says after XIT and Ci have been controlled for, no past values of XIT affect the expected value of YIT. It is more natural than a strict exogeneity assumption, which requires conditioning on future values of XIT as well. Let us now understand the dynamic unobserved effects model. An AR1 model with additional explanatory variable is YIT is equal to ZIT gamma plus rho 1 YIT minus 1 plus Ci plus UIT. This is our equation 4. So XIT is congruent to ZIT and YIT minus 1. Therefore, XIT minus 1 up to XI1 is nothing but is equal to ZIT, YIT minus 1, ZIT minus 1, so on up to ZI1 and YI0. And the sequential exogeneity assumption stated in equation 3 requires that expected value of YIT given ZIT and YIT minus 1 and so on up to ZI1 and YI0 and Ci is equal to expected value of YIT given ZIT and YIT minus 1 Ci and is equal to ZIT gamma plus rho 1 yit minus 1 plus ci. This is our equation 5. What is the hypothesis? The hypothesis is that H naught is equal to rho 1 equal to 0. So H naught we are denoting as rho 1 equal to 0, which states that after unobserved heterogeneity, Ci has been controlled for, including current and past Zit. Yit minus 1 does not help to predict Yit. So basically we are saying Yit minus 1 does not help to predict Yit after controlling for Ci and Zit. When rho 1 is not equal to 0, it means that Yit shows state dependence. Please note that the current state depends on last period's state even after controlling for Ci and Zit up to Zi1. Here assumption 5 is an example of dynamic completeness conditional on Ci, which means that one leg of Yit is sufficient to capture the dynamics in the conditional expectation. Neither further legs of Yit nor legs of Zit are important. Once Zit and Yit minus 1 Ci have been controlled for. Generally, if Xit contains Yit minus 1, then assumption 3 implies that dynamic completeness conditional on Ci. Now, assumption 3 does not require that Zi plus 1 up to Zi capital T be uncorrelated with Uit, so that feedback is allowed from Yit to Zi T plus 1 up to Zi capital T. If we allow Zis to be uncorrelated with Uit for all S, then additional orthogonality conditions can be used. What is a static model with feedback? Let us try to learn this in 2.3. Consider a static panel data model. Yit is equal to Zit gamma plus delta Wit plus Ci plus Uit, where Zit is strictly exogenous and Wit is sequentially exogenous. So it can be written as expected value of Uit given Zi, Wit minus 1 up to Wi1 and C1 is equal to 0. This we denote as equation 7. Wit is influenced by past Yit. So Wit can be written as Zit tau plus rho 1 Yit minus 1 plus phi Ci plus Rit. This is denoted as equation 8. In general, if expected value of Ri comma t plus 1 is equal to 0, it is easy to show that expected value of Wit plus 1 into Uit is equal to rho 1 expected value of Yit Uit, which is equal to rho 1 into expected value of Uit square and is greater than 0 under equations 7 and 8. And so strict exogeneity fails unless rho 1 is equal to 0. Keen and Runkel in 1992 argue that panel data models for testing rational expectations using individual level data generally don't satisfy the strict exogeneity requirement, but they do satisfy sequential exogeneity. In fact, in the conditioning set in assumption 2, we can include all variables observed at time t minus 1. Let us look at models with individually specific slopes in this section 3. The unobserved effects models have an additive unobserved effect that has the same partial effect on Yit in all time periods. Now, this assumption may be too strong for some applications, but still we do make this assumption. Let us look at a random trend model in this. Now, extending the standard unobserved effects model, Yit equal to Ci plus Git plus Xit beta plus UIT, where T takes the values from 1 to capital T. This we denote as equation 9. Sometimes the above equation is also known as or also called as random trend model, as each individual, firm, city and so on is allowed to have its own time trend. The individual specific trend is an additional source that leads to heterogeneity. So if YIT is the natural log of a variable, as is often happens in economic studies, then ZY is roughly the average growth rate over a period, holding the explanatory variable fixed. Then the above equation 9 is called as a random growth model. In many applications of this equation 9, we want to allow CI and GI to be arbitrarily correlated with XIT, but by allowing this correlation makes this model called as random trend model. Now, thinking of a program participation example, if one element of XIT is an indicator of program participation, equation 9 allows program participation to depend on individual specific trends or growth rates in addition to the level effect CI. For the random trend model, the strict exogeneity assumption on the explanatory variable is written as expected value of UIT given xi1 up to xi capital T, Ci and Gi equal to 0. Now this is our equation 10, which follows definitionally from the conditional mean specification. So expected value of UIT given xi1 to xi capital T, Ci and Gi is equal to expected value of YIT given xit, Ci and Gi, and this could be written to be equal to Ci plus Git plus xit beta. Now this we can denote as equation 11. In this equation, we primarily estimate beta. Now one approach to estimating beta is to difference away Ci, which means we take delta YIT equal to Zi plus delta xit beta plus delta UIT, where again T takes the values from 1 to capital T. Now this is our equation 12. Now here we are using the fact that GIT minus GIT minus 1 is equal to GI. The key strict exogeneity assumption in this case is that expected value of delta UIT given GI plus delta xi2 up to delta xi capital T is equal to 0 for the values of T again from 2 to 3 to capital T. Please note here the values of T ranges from 2 to capital T and not from 1 to capital T. Now this holds under assumption 10. Therefore, in order to estimate beta, fixed effects or first differencing methods can be applied to equation 12. In differencing the equation to eliminate Ci, we lose one period, so that equation 12 applies to T minus 1 time periods. In order to apply fixed effects and first differencing methods to equation 12, we must have T minus 1, T here is capital T, greater than or equal to T2, or capital T must be greater than or equal to 3. That means beta can be estimated consistently in the random trend model only if this capital T is greater than or equal to 3. Now, depending upon the properties which we are talking about of delta UIT, where T ranges from 2 to capital T, we can decide whether to use fixed effects or first differencing. Friedberg in 1998 provides an example using state level panel data on diverse rates and diverse laws. It shows how important it can be to allow for state-specific trends. Without state-specific trends, she finds no effect of unilateral diverse laws on diverse rates, with the state-specific trends, the estimated effect is large and is statistically significant. So I hope you understand how state effects can play an important role. Next section, which is 4, let us now try to learn about GMM approaches to linear unobserved effects model. First, we will start with 3 SLS versus standard panel data estimators. You know that random effects, fixed effects, and first differencing are still the most popular approaches to estimating unobserved effects panel data models under strict exogeneity of the explanatory variables. If the assumptions of these models fail, we can do worse than using an optimal GMM approach. So suppose first that following assumptions of random effects model are 1 or A, expected value of UIT given xi and ci is equal to 0 for t ranging from 1 to capital T, and B, expected value of ci given xi is equal to expected value of ci equal to 0, where xi is nothing but congruent to or equal to xi1 to xi2 to xi capital T holds, so that expected value of ci given xi is equal to 0. The model in composite error form can be written as yi is equal to xi beta plus vi, and this is our equation 13. The above stated assumption of random effects model says that xis is uncorrelated with vi for all s and t. In fact, any function of xi1 to xi capital T is uncorrelated with vit for all t. But we will only use the xi themselves. Let's now therefore denote xi0 as the row vector of non-redundant elements of xi, so that any time constant element appears only once in xi0. Here 0 is the superscript which we have used to differentiate from earlier xi. Then expected value of xi to the power 0 or 0 prime into vit is equal to 0, and all these are vectors here. Now t is equal to 1 to capital T. This orthogonality condition suggests a system instrumental variables procedure with the matrix of instruments, and these instruments are zi could be written to be equal to I capital T into Cronbach multiplication xi power 0 or xi0 as I pronounced it earlier. This is our equation 14. In other words, use instruments zi to estimate equation 13 by 3 SLS, or more generally by minimum chi-square. The matrix 14 can contain many instruments. If xit contains only time varying variables, then zi is t into t by k. With only k parameters to estimate, this choice of instruments implies many over-identifying restrictions even for moderately sized capital T. Note that using many over-identifying restrictions can result in poor finite sample properties. In some cases, we can reduce the number of moment conditions without sacrificing efficiency. Eam, Han, Smith and Wooldridge in 1999, which is also in abbreviated form written as IASW, they show the following. They show that if omega hat has the random effects structure, which means we impose the random effect structure in estimating omega, then 3 SLS applied to equation 13 using instruments which are zi equal to pt xi qt wi, where we can write this as equation 15. pt matrix is denoted as jt into jt prime, jt inverse jt prime, and qt is equal to IT minus PT. Here all these T's are capital T's. Now Zt is defined to be equal to 111 prime and Wi is T into M submatrix of Xi obtained by removing the time constant variables, which is identical to the random effects estimator. The column dimension of matrix 15 is K plus M. So there are only M over identifying restrictions in using the 3 SLS estimator. The algebraic equivalence between 3 SLS and random effects has some useful applications. First, it provides a different way of testing the orthogonality between Ci and Xit for all t, small t. Second, it provides a way to obtain a more efficient estimator when assumption A, which is expected value of ui prime given xi and ci, is equal to sigma u square into I capital T into B into E expected value of ci square given xi. Now all of this could be written to be equal to sigma c square or sigma square c. This is our equation 15.1 of random effects model. Now here please note that we assumes that the conditional variances are constant and the conditional covariances are 0, whereas B is same as variance of Ci given Xi is equal to variance of Ci, which is a homoscedasticity assumption on the unobserved effects of Ci. This does not hold. We are saying that in all this we are assuming that random effects model does not hold, and A and B are those conditions. So if omega does not have the random effects structure, then the 3 SLS estimator that imposes this structure is inefficient. In that case, an unrestricted estimator of omega should be used because an unrestricted estimator of omega is consistent with or without the random effects structure. 3 SLS with unrestricted sig omega hat and IVs, which are instrumental variables in matrix 15, is no less efficient than the random effect estimator. Further note that any 3 SLS estimator is inefficient relative to GMM with the optimal weighing matrix if expected value of Vi prime given Xi is not equal to expected value of Vi prime. Therefore, if the above mentioned assumption of random effects model 15.1 fails, then minimum chi-square estimation with IVs in matrix 15 generally improves on the random effects estimator. Alternatively, we can say that we can gain asymptotic efficiency by using only m less than or equal to k additional moment conditions. M is capital, K is capital, so all these are capital. Let us now understand in section 4.2 Chamberlain's approach to unobserved effects models. This approach is used to estimate the linear unobserved effects model due to Chamberlain, which were given in 1982 and 84 and related to Mundluck 1978. We will continue with the strict exogeneity assumption on Xit conditional on Ci, but we will allow arbitrary correlation between Ci and Xit. Thus it follows fixed effects environment and Xit contains only time varying explanatory variables. In case of fixed effects and first differencing transformations, Ci gets eliminated and produce consistent estimators under strict exogeneity. Chamberlain's approach is to replace the unobserved effect Ci with its linear projection onto the independent or explanatory variables in all time periods plus projection error. So suppose Ci and all elements of Xi have finite second moments we can write Ci equal to phi plus xi1 lambda 1 plus xi2 lambda 2 so on up to xi capital T lambda t plus ei. This is our equation 16, where phi is a scalar and lambda 1 to lambda t are 1 into k vectors. The projection error ei by definition has zero mean and is uncorrelated with x1 to x1 capital T. There is no assumption made about the conditional distribution of Ci given xi. In particular, expected value of Ci given xi is unrestricted as in usual fixed effects analysis. Plugging equation 16 into the following model, yit equal to xit beta plus Ci plus uit, where t again varies from 1 to capital T, we get for each t yit equal to phi plus xi1 lambda 1 so on up to xit into beta plus lambda t, plus it must continue and it will continue up to xi capital T into lambda t plus rit. Now this is our equation 17. In this, under assumptions of fixed effect 1, the errors rit are equivalent to ei plus ui and satisfy expected value of rit equal to 0 and expected value of xi prime rit equal to 0 for all t ranging from 1 to capital T. This is our equation 18. However, unless we assume that expected value of Ci given xi is linear, it is not the case that expected value of rit given xi is equal to 0. We can write the system 17 for all time periods t as a scalar and matrix form. You can see on the left hand side we have the scalar of yi1 to yir, and on the right hand side we have the matrix of 1 xi1 xi2 up to xt1, and similarly we have the scalar of the parameters from xi lambda 1 to lambda r and beta, and we have the residual scalar of ri1 ri2 up to rtr. This is our equation 19. We can write the system 17 for all time period t as a scalar and matrix form, and you can see on the left hand side we have yi1 yi2 up to yi capital T, and on the right hand side we have the matrix of 1 xi1 xi2 xit up to and xi1, and this goes on, and the last diagonal value you can see is xit. The product scalar you can see is the scalar of parameters starting from xi lambda 1 lambda 2 up to lambda t and beta, and then we have the residual vector of ri1 ri2 up to rit. This is our equation 19. Now this can also be rewritten as yi is equal to omega I into theta plus ri. Now this is our equation 20, where omega 1 or wi, whatever way you may define it, is t into 1 plus tk plus k, and theta is equal to 1 plus tk plus k into 1 vector. From this equation 18, you can see that expected value of wi prime ri is equal to 0. So system OLS is one way to consistently estimate theta. The rank condition requires that rank of expected value of wi prime wi is equal to 1 plus tk plus k. It suffices that the elements of xit are not collinear and that they vary sufficiently over time. While system OLS is consistent, it is very unlikely to be the most efficient estimator. It is important to impose further assumptions, otherwise not only scalar variance assumptions which means expected value of Ri prime equal to sigma r square into capital IT becomes highly unlikely. But also the homoscedasticity assumption fails, which is that expected value of Ri prime given xi equal to expected value of Ri prime, which is our equation 21. It will fail. This 21 equation shows our homoscedasticity assumption. The assumption in equation 21 is violated when expected value of ui prime given ci and xi is not equal to expected value of ui prime. Now, if expected value of ci given xi is not linear in xi, or if variance of ci given xi is not constant. Now, this basically means that if the assumption is stated in equation 21 does happen to hold, in that case, feasible GLS is a natural approach. GLS here means generalized least square. The matrix omega is now equal to expected value of Ri prime and can be consistently estimated by first estimating theta by system OLS and then proceeding with feasible GLS. Now you can see on the contrary, if this assumption fails, a more efficient estimator is obtained by applying GMM to equation 20 with optimal weighing matrix. In equation 20, there are 1 plus t into k plus k parameters, and the matrix of instrument is t into 1 plus tk. So there are t into 1 plus tk minus 1 plus th plus k is equal to t minus 1 into 1 plus tk minus k over identifying restrictions. Please look at these notations very carefully. Now, testing these restrictions is precisely a test of strict exogeneity assumption fixed effect 1, and it is a fully robust test when full GMM is used because no additional assumptions are used. Chamberlain in 1982 works from the system 19 under the assumption 18, but he uses a different approach for estimation, which is called as minimum distance estimation. Let us now discuss about panel data application in matched pairs and cluster samples in our section 5. The unobserved effects structure is not a consequence of repeated cross sections over time. One simple data structure is a matched pair samples. Now this can be shown by an example. We take the case of sibling data, which are often used in the social sciences in order to control for the effects of unobserved family background variables. For each family I in the population, there are two siblings. It can be explained as follows. We can write yi1 equal to xi1 beta plus fi plus ui1, equation 22. And similarly, yi2 is equal to xi2 beta plus fi plus ui2 as equation 23. The above equations are for sibling 1 and 2 respectively, and fi is an unobserved family effect. Here, the strict exogeneity assumption means that the idiosyncratic error uis in each sibling's equation is uncorrelated with the explanatory variables in both equations. For example, if y denotes log Viz and x contains years of schooling as an independent or explanatory variable, then we must assume that siblings' schooling has no effect on Viz after controlling for the family effect on schooling and other observed covariates. If fi is assumed to be uncorrelated with xi1 and xi2, then in this case differencing across siblings will be an appropriate strategy to remove fi. Under this strategy, x cannot contain common observable family background variables as these are indistinguishable from fi. The IV method developed to account for omitted variables measurement error, and simultaneity can be applied directly to the difference equation. A matched pair sample is a special case of cluster sample. A cluster sample is typically a cross-section on individuals like families, firms, etc., where each individual is part of a cluster. Observations within a cluster are thought to be correlated as a result of an unobserved cluster effect. The unobserved effects model can then be represented as YIS equal to XIX beta plus CI plus UIS. Now this is our equation 24. In this above equation, I indexes the group or cluster and S indexes units within a cluster. In some cases, an unobserved effects model or cluster sample is called a hierarchical model. In cluster samples, the number of observations within cluster usually differs across clusters. For cluster I, the model can be written as Yi is equal to Xi beta plus Ci Jgi plus Ui. This is our equation 25. The row dimension of Yi, Xi, Jgi and Ui is Gi, the number of units in cluster I. The dimension of beta is k into 1. So while applying panel data methods, we assume that the number of clusters n is large because we fix the number of units within each cluster in analyzing the asymptotic properties of the estimators. Since the dimension of the vectors and matrix in equation 25 changes with I, so we cannot assume an identical distribution across I. The strict exogeneity assumption in the model 24 requires that the error term UIS be uncorrelated with the explanatory variables for all units within the cluster I. This assumption is often reasonable when a cluster effect Ci is explicitly included. And if we assume Ci to be uncorrelated with Xis for all S, where S varies from 1 to Gi, then pooled OLS across all clusters and units is consistent as capital N tends to be infinitely large. So what have we learned? Let us summarize our learnings of the day. To summarize, in this module, you have studied about unobserved effects model or models without a strict exogeneity assumption, in which we have learned about dynamic unobserved effects model and static model with feedback. You have also learned about random trend model, which is sometimes called as random growth model. You have also seen how to apply panel data methods in case of match pairs and cluster samples.